Ting, the new way everyone is getting their cell service. No overage penalties, great rates, keep what you do not use, no contracts, and someone will actually pick up the phone when you need support. Use our link and get $25 off your first month's service or your new phone. Just go to tech-zen.tv/ting to save $25. Hello and welcome to another episode of Let's Make It. This is episode number 25, and this week I'm here with Bob again, and this week we're going to talk about how to make a thermostat, and we're going to show it to you in two different kinds of temperature sensors. Bob did the most popular one probably, and then I took the temperature sensor that I did in the sensor episode and integrated it into a thermostat, and so we're going to show you two different ways of doing that throughout the two different segments of the show. And this week we're going to get started with Bob. But before we do that, let's make sure we say hi to Bob.
Hello, Mike.
All right, how you doing?
I'm good.
How have the storms been down there this year?
Well, the tornadoes were tough a month ago. Not as bad as Oklahoma, but we had a few around here, but it's Texas in the summertime, so it was. I think we hit 100 today, so not bad.
Oh yeah, it's not too bad. Then
No.
It's not quite summertime yet, where it's quite so dry either. I just
Yeah,
thought it was cool.
not yet.
Yeah, I was just wondering about cause we've had this week storm after storm after storm, it's right in a row. So it's like every night we're recording a show, there's a storm around, it seems like. So, all right. So the first thing we're going to do, Bob, is we're going to go over and we're going to watch your demo. You gave me a video, so I'm going to go ahead and play the video, and we will have you kind of go ahead.
Okay. Well, I have the circuit set up. Let me switch to it real quick just to show, just so we can see what's going on.
Okay.
So I've got the LCD screen, and then this little guy right here that you can hardly see is an LM35 sensor, and it reads in Celsius, and the code will show that. And then this little connection right here, that right there, that's just for me to disconnect it, because in this video that we're going to watch, there is a place where I unplug it so you can the code will check to make sure there's valid data. So that's what that connection is for, and that's the little sensor, and then we just put the output to the LCD screen, and it's a fairly simple little circuit, and then in your demo, you do something with the data as you're reading it. So this is just a demonstration of how to read the LM35.
Right. So let's go play the video real quick.
So let's look at the video.
And let me hit play.
So here we have two little welcome screens. Pretty self-explanatory. And now here it's reading the data. It's reading off one of the analog pins. And now I have a little piece of ice that I'm going to put on the circuit. And I have to do this quick because I don't want to have it melt and get water in my breadboard. But as it cools down, it tells you that it's cold and it's time to turn on the heat. And then it's back into normal temperature range. And then here I'm just using my fingers to heat it up a little bit, just to show that it is reading. And then when it gets warm, it says that it's hot and it's time to turn the AC on. And then the last piece is where I disconnect the circuit, and it warns you, and that blinking that's on purpose. And then we're back to normal. And I found it to be, I used the setup right out of the Arduino playground, and found it to be accurate and correct, and actually really easy to use.
All right. So yeah, that was all available right off the playground. So nothing really special. And I think
nothing real special.
We want to note kind of in here that this is using just an analog pin. There's no special data calculation as far as sending digital data. It's basically reading off an analog pin.
Yeah, it's just reading the analog pin, and there's one little calculation to turn it from the analog reading into a Celsius measurement. And then, of course, I do a standard Celsius to Fahrenheit mathematical conversion.
Right.
And there is an LM34 sensor that does the same thing, only it actually will read the data to you in Fahrenheit.
Right. So the one you use actually reads it to you in Celsius, and you have to convert it for Fahrenheit.
That's right.
All right. So let's go walk through the code. And let's see, we'll scroll down a little bit here. And this, what is this chip cost? About $2, something like
that? Something like that, yeah.
Yeah, a lot less than what my digital one cost.
Next to nothing.
Right. All right, so at the very top here, you're only including 2 libraries, so it shows you don't need anything special. Just the liquid crystal and the wire.h, which both control the liquid crystal display.
Yeah, and the liquid crystal library is the same one that we used. It's funny. You and I both worked on the SaneSmart LCD screen, and episode 5, you made some changes to the code. And interestingly, I made basically the same changes, but I did add one additional function into that library. So where I keep all the code on GitHub has my slightly modified library, but it's basically your code plus one function.
All right.
Because both of us had the same problem with the SaneSmart code. It just didn't work. So we had to modify the library.
All right. And we come down and where you're setting columns and rows here.
That's right.
And you're using them right here to set the liquid crystal display. One of the things about the SaneSmart, I think their documentation doesn't say it's 3F, but it is 3F. If I remember that correctly. And then you set your temperature pin. So you're using analog 1 as your input for your temperature pin.
Right. And I could have used any of the analog pins, and that's just the one I picked.
Right. And if you're using an Uno, you couldn't have used 4 and 5. Is that correct?
You can, but you have to move I'm using the standard
library for 2
standard library for
the wire.
For the wire. So you could have reassigned those pins, but I didn't see any reason to, so I didn't.
Right. All right. So we're going down through setup, and we just do the LCD init. You reset it, turn the light on so we can read it, and then
that's right.
And then we do the initial demo screen, which is the welcome and the GitHub information.
That's right.
Then you do the LCD clear, and then we come to a funny one. So this is one you need to explain because it's something that you wouldn't have to do, but it makes things better, right?
Well, this is a little piece that I found on the playground, and they said that if you change the internal reference of the analog pin within the Arduino, you could get a much more precise measurement off of it. So I made this one little change, and that's exactly what I saw, a much more precise reading off the sensor. Now, the cost of that was I did lose a little range, but since since this demonstration is based off of a for a heater, a heater, air conditioning unit, a thermostat replacement kind of project, that was actually a good thing. So the reference goes from 0 to 110 degrees.
Okay. And if it's that cold or warm in your house, you have other problems.
You have some other problems. That's right.
All right. And then we come down into the actual loop function, and you define some variables. I assume loop delay is your delay that you're waiting in the loop. It makes sense,
yeah.
Right?
As this runs, it's checking the sensor once every second.
All right. And then you define the reading variable and 2 temperature variables. One, it looks like it would be Celsius, and one in Fahrenheit. And I do want to note that you have them floats, not ints, because they have decimal places in them.
That's right. If you change it to the integer, then you just get whole numbers, and you lose the decimal place, which kind of defeated the purpose of going to a more precise measurement.
Right. All right. Then here comes the actual work we're going to do, right?
Right, that's it. And so we have one. We grab the reading off the analog pin, And this formula right here is straight off the Arduino playground, where we take the reading and divide it by 9.31.
All right. Was there any description of why 9.31 in there?
There is they show the calculation and how they arrived at that calculation. I did not put that explanation here.
That's fine. So if you're interested in knowing why, go to the Arduino playground, and they'll explain why.
That's right.
And this number was different depending on which reference you're using, correct?
That's right.
So the internal reference number is 9.31. If it's not internal referenced, then there's another number you put in there.
Yeah. If you don't use this, if I remember right, it was 5 volts times the reading times 100, and whatever the product of that multiplication is, you divide it by 1024, and that gives you the temperature in sensor in Celsius.
Okay.
So you could use this sensor with 3.3 volts, and then you could simply change the formula and get a accurate reading again.
All right. And then you convert the Celsius to Fahrenheit, and this is a very commonly known calculation.
Standard calculation.
And there's a couple ways people have done this. So I've seen 9 divided by 5 times temp in times 9 divided by 5, like you did it. Then you got to add 32.
It all comes out the same. That's right.
All right. And then we come down and we have some debugging code in here. And then we go. Yeah. So you're validating you have a valid reading. So you just mentioned about the reading being 0 to 110, but you have it here as 307.
The value off the analog pin, according to the documentation, will range from 0 to 307.
Right. So
and
you got to
within
remember
that range.
Right.
You'll get the 0 to 110 degree range of temperature, but the analog pin is going to show those values. So here I just make sure that I'm within what is supposed to be the correct range of data, and then if I'm not, then it pops up this message.
Okay.
So I check it and then I do something.
Right, and this is where you showed in your video about it flashing because you unplugged it. So when you unplugged it, do you know what value it was sending?
When I was debugging this, I got values in the tens of thousands.
Okay, so it's definitely not anything close to this.
Completely out of range.
Right. All right. And if it's out of range completely, you basically are blinking the display. You see here, you're turning it off and back on.
That's right. Yeah. Turn off the backlight, turn back on the backlight, and show the message that it's invalid data. And I completely avoid the portion of the code where I'm doing something with the temperature.
Right. All right. And you do that, how many times do you do that? Oh, you do
well, I'm looping through this, once a second.
Right. I gotcha. All right. And if the data is good, then you're going to set your cursor and say the current temperature is, and you're going to display it in both Celsius and Fahrenheit.
That's right. And I kind of wrote this out in a long way just to show how all the pieces were being put together. The char 223, that's actually the character for a degree symbol.
All right. That's good to know. And
so this could have been written in a much more compact way, but I wrote it out on purpose to show all the pieces.
All right. And then you're checking your temperature, and if it's greater than or equal to 82, you're going to say, wow, it's hot, turn on the AC, which we saw that in the video when you had your finger on there.
That's right. Or with the finger on there, that's right. And then when I had the ice on there, then it got below 68 and told you that it was cold. And turn on the heat.
All right. And then if it's not either one of those two, you're doing the clear row function to clear out the text that's on there.
And that's basically just because if the text has been left from one of those other messages,
right, it stays there.
I want it's not going to get cleared off unless I specifically tell it. So every place where you've got, something with the temperature, that's where you would do something, and you're going to show that in your code later on.
Right. All right, and then we delay, and we just do the loop delay.
And then repeat it again.
And do it all over again, right? And so at the very bottom, you have your initial demo screen, which basically shows what we had on the screen. the sensor demo as seen. Let's make it. You wait for 5 seconds, and then you do the link to GitHub, and then you are done. And then you've created these other functions to make it easy to center things in the. So print centered basically takes the length line, divides it by 2, and then moves it left that many times basically, and then puts the text out to the screen. I think we've talked about these functions before at some other point.
Yeah, these are convenience functions that I wrote for an LCD screen, which just prints something centered, printed, right justified, left justified. Just make it a little, my code a little more compact, because you see I wrote, those 2 screens with basically, less than 10 lines of code total.
Right.
So. They're just convenience functions, and they're actually part of something else that I'd written elsewhere. And that's why I had to include my library with the one additional function, or your library with the one additional function added.
All right.
To be compatible with this LCD code. But really, reading the analog pin, really all it is 3 lines of code in here.
Right. So the rest of the stuff's just the display.
That's right. You set the internal reference, you read the analog pin, you make one calculation, now you've got a temperature.
All right. And then here's the clear row, and that's it. It's toward the bottom of the code.
That's right.
All right. So before we jump into the next segment, we want to remind you that we are moving our YouTube channel to one big channel for the whole Checksum TV network. So if you've been watching us on YouTube, I've been telling you, I'm going to keep reminding you of this for the next couple of weeks yet still, that we are moving all the videos, so they only will be on the new YouTube channel in the next couple of weeks. So if you've been watching us on the Let's Make It channel, you need to go to youtube.com/TechZenTV and subscribe over there, because we'll start putting these shows over there only in the next couple of weeks. So you don't want to get lost. Make sure you go do that right now. Just a real quick reminder that I wanted to bring up. Now, we also had a viewer question this week that Bob has worked up a little presentation to explain what it is. So we basically had somebody want to know what forward voltage is, and you hear us talk about that. And so Bob's going to go through and he's going to show us and explain to us what forward voltage is. So let me go ahead and get this up here. And we'll let Bob go ahead. So forward voltage is what we're talking about.
So this is forward voltage, and this is a question from viewer named Matt. So thank you, Matt, for bringing this up. The basic definition of forward voltage is that it is the minimum voltage that you need to light an LED. So if you've got an LED and we're going to use this in an example in a couple here in just a moment, where the LED is a 3-volt forward voltage device. Well, if you supply that LED with 2 volts, you're not going to have any light. You have to get past the 3 volts. The other nice thing about it, which is actually very convenient, is that LEDs, the voltage does not change with temperature. So the forward voltage is very constant across a temperature range, which makes using LEDs very easy. So why is forward voltage important? And this will actually get to the problem that we were talking about last week. We need the forward voltage to make sure that we give the LED the correct amount of current, because in any LED you've got to have a resistor, otherwise you blow out and burn out your LEDs. And as much as I like the smell of burnt electronics, it is something that I try not to do. But we need to know the forward voltage, what the maximum current of the LED is, and of course we need the supply voltage. So here we have one little LED, and we're going to see this LED here in just a second. It's one that I have sitting around, and it's spec'd at 3 volts and 20 milliamps. And we're going to just use Ohm's law to calculate the correct resistor. And the calculation is fairly straightforward, and it's right there. So in this case, we need a 100 ohm resistor to make sure that we stay at 20 milliamps. And as long as we use something 100 or greater, then we don't have to worry about burning out our LED, because if the resistance is greater, then the current is lower.
Okay, before we go to the next page, can we talk a little bit about Ohm's law? Because I just want to make sure that people that are watching the show that aren't necessarily into electronics, but more into making things like, Arduino type projects, understand a little about Ohm's law. I don't want to go into great detail, but it's basically the combination of three things that always equal each other.
Yes, the whatever the current is times whatever the resistance is going to give you the voltage. And in this case, we've rearranged the formula, so we want to calculate the resistance. So we're going to take whatever the supply voltage is, and we're going to subtract whatever the forward voltage is. And then we're going to divide that by the current. And in this case, it's the spec maximum current. And of course, we have to, these calculations are all done. We can't just put in 20 and have it work. It's got to be in amps, not in milliamps. And that gives you, that calculation will give you the 100 ohms. So yeah, Ohm's law, it's, if you're doing anything in electronics, then Ohm's law, you're going to run into it all the time. It's the most basic function in electricity.
And if you don't know what it is, you probably should go out and look it up, because it's definitely an important thing to know.
That's right. You've got to know it.
All right, so we'll go on here now.
So here I made a small little circuit, and since we talk about Arduinos here, I'm going to use an Arduino, and really all I'm doing is nothing more than using it to supply current to an LED. But I wanted to, I did want to put out, show the schematic and what it looks like on the breadboard.
All right.
And then this next page, the first picture you see in the upper right, I've got my little multimeter there, and I've switched it to check for resistance, and my 150 ohm resistor is actually reading 146.1. And then just to double check this demo, I checked my power supply off the Arduino, and I'm getting the 4.69 volts. And this Arduino, this is actually, something that's nice to know about an Arduino is that that's plugged into a USB port right there. And you're not going to get, even though the pin says 5 volts, you're not going to get your full 5 volts. You're going to lose a little bit in the power conversion within the Arduino. So 469 is typical. But I did double check my voltage. And then the last screen, one interesting thing is if you have the LED on, you can check the voltage across the LED. So if you look carefully in that picture, you can see that I've got my pins on the LED, and I'm reading a forward voltage of 302. So it's right on spec. So using the formula we got before, we can calculate that I'm running 11.4 milliamps through that LED as this picture was taken.
Which is definitely in the safe range, because 20 is the max.
That's right. So I used a little higher resistance resistor and got a lower current reading.
All right, and that's it.
And that's it. So, Matt, great question. Thank you.
Yeah, keep those kind of questions coming. We want to make sure that if you have those kind of questions, we love to hear them, because we'd like to answer them just as much as we like to hear them.
That's right.
So thank you, Matt, for asking the question. And if you have questions like that, please do not hesitate to let us know. And also, we got an email of some other suggestions for shows. We definitely appreciate that. Gives us more ideas to things that we can do in future shows for you as well. All right, so like I said, I took a slightly different approach to this, and it looks more like a mess than what Bob's does, but I actually used a digital sensor. So let's go over and we'll show you what I have. So the original request, or we got a request. The original thing we wanted to do was a thermostat. Then we got the request of how to do it via XP. So what you see here is two Arduinos. You see the Arduino up here and an Arduino over here. Both have XPs. And this XP is actually on the breadboard because I needed the pins open so I could get to them. So there's two XPs. These are not connected in any way. They're both connected to a USB power supply only. And we're going to show you how they can communicate with each other. So right now, what you see is three lights. When this is a yellow light when it's on, a blue and a red. The yellow light represents a fan, like your internal fan on your HVAC unit. Blue represents air conditioning, and red represents heat. And then over here you have three buttons, and red means to turn up the temperature, blue means to turn down the temperature, and white is the mode button. And then this little blue thing right here is the actual temperature sensor, and we just showed this in another episode. I don't remember what episode it was now. With sensors, and it's electronic. It provides both temperature and it provides also humidity. And then you see the display right here, and I'm showing you the current temperature, the current humidity, and right now I have it in heat mode, so the light's turned off. So what I'm going to do is I'm going to change this to a different mode. That's cool. And auto is basically hot and heat and cool. And there's a delay here for 5 seconds, so you just don't want to change things around on relays to control your HVAC that real quickly. So there you saw both the fan and the AC. You can barely see it's on, but if you cover up the yellow, it's there. The blue AC is on as well. And you also saw on the remote one, the same thing happened. And this is all done via XP. So in here, you can adjust your temperature. If you want to adjust the temperature down or the heat up a little bit, you can adjust all that stuff here. We can go into just the fan mode. So again, in 5 seconds, you'll see that the AC should turn off, but the fan will remain on. So let's give it a couple seconds here, and it should come back and turn those off. All right, there you go. So now it's just the fan is on because we're in fan mode. And we go into the next mode. And here we are, cool. So we know it's going to be cool with 77 degrees in the room right now, and I have it set for 71. So in 5 seconds, that should turn on, and there goes the AC. And then we also have heat, and I'll go ahead and let the heat come on. Right now there's no heat to be running because the temperature's set at 71 and it's 77 in here, but I'm going to go and turn it up to make it think it needs to come on. So now everything's off. I'm going to crank up the heat to 79. No, I went to 80, sorry. Oh, it's one too far. That's okay. It'll still turn on the heat. There we go. So now we have heat and fan turned on. Now I don't have an LED for emergency heat, but the code does have the ability to support emergency heat, and there's a pin I have to hook up. I haven't done that. And we're going to go to the next mode, which is options. So the only option I have really set in here is I can do both Celsius and Fahrenheit. Right now you see it's in Fahrenheit. So when it's in options mode, these two buttons change the mode. So I'm going to now put it into Celsius mode. So it's 25 degrees in here, 26 degrees in here Celsius. And I can put it back into Fahrenheit by doing this. So if I leave it in Celsius mode and I go to the other modes, like auto, for example. Oh, let's go past auto. It's not going to work right. So we're going into cool mode. And you see it's set for 21 and it's currently 25 in here. So I should still turn on the AC. So let's go turn it back to Fahrenheit because I can't relate to Celsius. So there we are.
Come on, Mike. You don't know your Celsius?
I have nothing against it, but just, I don't use it enough to be able to relate to it. So that's pretty much what we did with the thermostat options. And you can see here, everything's happening very quickly between these two. So, and it's all done via Zigbee, completely wireless. And depending on what kind of Zigbee or XB, I'm using XB chips, but depending which one you have will determine how far it goes. These are not very far. I think I've gotten them at least 30 feet away, and it worked fine when I was setting it up in here. But I don't know what long distance it really is. But you can get it with the nice antennas on them if you want to go farther. So let's go walk through the code. And I do want to say while I'm getting the code up, there is some concern about this because you're actually going to be touching live electricity. And you need to be very, very careful when you do that, because you can definitely hurt yourself, and we wouldn't want that to happen. We also want to make sure that you know that just because we've shown you this doesn't mean you should do it. You're totally at your own risk to do it. But you just remember, there's the possibility you could either ruin your HVAC system or even hurt yourself, even fatally hurt yourself if you are in the mains area. All right, so let's go ahead and walk through this code. And I put a couple of notes in here, and my brother-in-law is an HVAC guy, and he basically recommended I do not put the color of the wires in here because everybody has different colors of wires. So I'm going to walk through this a little bit. But I have noted in here the wires and what they do. And what I'm probably going to do is, well, red's always the same thing, green's always the same thing. But probably going to take out some of the other ones, because depending on who put your system in, they can use different colors. Red's always 24 volts. Green's always the fan. Typically, yellow and white are always the same, but not always. You can't count on that. So what he told me to tell everybody was, if you're going to take off your thermostat, it is best to pull it off the wall a little bit, cut the wires that go into the thermostat, and leave them attached to the thermostat so you know what color was used for what. And then just strip the ends off and put them into the whatever else you want to connect it to. So the pins that you have the 24 volt feeds, you have a wire for first stage cooling, which is pretty much all most homes have. They don't have a second stage, but basically if the 24 volts is fed and attached to this wire, which is typically yellow, the cooling system will start. Now, like I said, most homes don't have a second stage, but commercial cooling systems sometimes do have a second stage. So it's something to remember there. And then we have another one for the fan. And again, this is typically green. It's pretty consistently green. And if you add 24 volts, attach 24 volts and contact closure it over to that wire, it turns the internal fan on. So that's why you see two of my lights coming on together, because if you're running AC, you need the fan. Otherwise, you're not going to be just not moving the stuff around. And then we have a wire for first stage heating. And again, most places don't have second stage heating unless you're commercial. So if you send 24 volts down that wire, the system will come on and it will turn on heating. And then there's another wire for second stage if you have second stage, because then unless you're commercial, most places don't have second stage. And second stage is not emergency heat. There's actually a separate wire for emergency heat. In the case that you have like a heat pump, you would have an emergency heat wire for that. So the next two are actually heat pump only wires. One of them is for reversing valve when you're running AC. And basically, if you are running a heat pump, you need to tell the outside unit which direction the freon should be flowing, and these reversing valves do that. Now, there's sometimes you have a wire for reversing valve for both cooling and for heating, but more often than not these days, you only have one for cooling. So it assumes you're heating unless you energize that wire for cooling, and then it reverses the valve. Some systems still do have two wires, but not many. And okay, let's go down a little bit here. I defined how I use the pins. And there's one thing, and we're going to get down here a little bit. You're going to see I use input pull up, and I'll explain why I do that when I get down to there. So here you see the pins I'm using. The Zigbee is using the transmit and receive pins. The pin number 3 goes to the temperature down. Pin number 4 goes to temperature up. And pin 5 goes high when the fan should run. Pin 6 goes high when AC is calling. 7 goes high when heat is calling. 8 goes high when emergency heat is calling. And then pin number 9 connects to the mode button. And the temperature sensor itself is actually on pin number 11. Again, I want to remind you that this could be very dangerous if you're actually touching your HVAC system. It is live. You could hurt it or yourself. And let's see, come on down here. So I included the same two libraries that Bob had in his, the wire and the crystal. That's how we're controlling the LCD display. But I have one more. This sensor I'm using actually has a library out in the playground. It's called DHT11, which is basically a one-wire interface to a temperature sensor. So we include that. And then we're going to set some of our defaults for a thermostat. So a few things. When it first starts up, it's going to come up with a cool temperature of 72 and a heat temperature of 70. So you see my two defaults right there. And then I have this minimum and max. So I have a minimum cool temperature. The coolest you can make it is 60. It will never let you make it any colder than 60. And it won't let you make it any hotter than 85. So here's my max heat temp, which you'll see that in the code where I check for that. And then I have emergency heat degrees. So what this is if I see that your temperature is set for 75 and it reaches 72 in your house, I'm going to turn on emergency heat because I don't think that the heat's working properly or it's not working efficiently because it's too cold outside. So that's an automatic thing. So you don't have to go into emergency heat mode if you don't want to. It'll take care of it on itself by itself. And then we have a run mode, and then we have our measurement mode. So measurement mode equals false is actually equal to Fahrenheit. It's equal to true. It's equal to Celsius. And then we come down and I have a couple of things I use. You'll see these variables throughout the code that I'm using to keep track of things. And I'm going to explain a little bit more what I do with waiting loop and why I do that down a little bit later. Here I'm defining the pins, and I call these out above. So mode, temperature up and down, fan, run pin, AC run pin, and heat run pin, and then the emergency heat run pin. I have 6 modes defined, so my maximum modes is equal to 6. I have auto, fan, cool, heat, emergency heat, and options. And probably the one I should have added and I didn't is off, because there's no easy way to turn off the lights except for set or something and just the temperature. Okay, so liquid crystal right here is define the display. I'm defining the temperature sensor right here. And we come down here, we attach the temperature sensor to pin number 11. And I'm going to set these pin modes here for all the different things. And I mentioned input pull up. So the reason I'm doing this is when you press the button, it's actually connecting it to ground. So I want an internal pull up resistor attached to this pin so that it reads true unless you're pressing the button, then it reads false as a return. And you'll see that in my code when I get down there a little bit. Then I have the LCD init, and I turn the backlight on, and then serial begin is set up. That's how I'm communicating through the Zigbee, is 9600 baud to the other remote side. All right, so now we come down to the working loop, and the first thing I'm going to do is check the mode button. So if the mode button is not true, which means it's actually pressed because I'm taking it to ground, and it's coming back as a logic 0. Then the button was pressed, and here's where waiting loop comes in. So the whole idea of the waiting loop is you don't want to make changes immediately when somebody's pressing the button. If you're scrolling through the different modes or changing temperature, you don't want to pass by the value where it should have turned something on and then pass by where it turns something off. You don't want to turn things off and on really fast. So what I do in the waiting loop is I set this back to 0 saying a button was pressed. And then I start my waiting time over again so that you have time to make changes to the thermostat before it makes any decisions what to do with the temperature. So that's the first thing I do here. And then I come down here and you see I clear out these areas. And the reason I clear out these areas is depending what mode you're in, certain things will change. And it looks funny if you don't clear out the area because what's coming in can be shorter or longer than what was in there before. And then I increase my mode by 1. Like I said, we have 6 run modes defined under max mode. So if my mode goes over the maximum, I go back to the beginning, which is 0. And the 0 is the automatic mode. And then in the temperature up button, again, a button was pressed. I'm going to set my waiting loop back to 0. And if I'm in run mode 5, which this is the options mode, I'm going to change my measurement mode to true, which means I set it to Celsius. And I'm going to, at that time, also take and blank out the area where the temperature is because Celsius is typically shorter than what the Fahrenheit numbers are. And if it's not in mode 5, I'm going to go and I'm going to increase the temperature. And the reason I'm calling a function you'll see later is I'm increasing the temperature for the mode that I'm in. So rather than putting all the logic here saying what mode am I in, I just do it one place later on. And then we do the temperature down button, which basically does the exact opposite of the temperature up button. If it's not run mode 5, we decrease the temperature. And again, we call another routine to determine what mode you're in and what gets changed. And if you are in run mode 5, then we're going to set it back to Fahrenheit and clear out the area again. And then we come down and we actually get to do the work. So here we basically are reading the values from the digital chip right here. So this sets the CHK is the return. Basically, it's a status return. And I come down here and I say if a status is equal to 0, that means that everything was good. I got back data, no problem. So if I'm okay and everything's good, I'm going to set the cursor, print out the word temperature, and depending on what measurement mode is set, I'm either going to display the temperature, and you see this is actually a structure, so it's actually like a library function or a library value, and so I'm going to display the temperature and put the little c after it. And if it's not in Celsius mode, I'm going to call a function called Fahrenheit, which takes this temperature value in Celsius and converts it to Fahrenheit for us. So there's no calculations needed to generate the Fahrenheit. I'm storing the current temperature, and because I use this later, as Fahrenheit. So everything I do internal to this is done in Fahrenheit, not Celsius. So that's something else to kind of remember as well. So I set the cursor. I am then going to display humidity, and I am going to do the dht11.humidity, which is a value set in the class, and a %sign. I'm going to set the cursor, say what mode I'm in, and here I'm doing is printing out the modes array that we saw above. And then there's a function called current settings. I'm going to walk through that. This was just an easy way of doing a little bit cleaner way of handling that. Now, like I said, a 0 means that there was no error, but it does send back error codes. So if you're having problems with this chip, you can uncomment this area, and this will actually print on the screen what error code the chip is sending you. Typical ones are timeout and checksum errors. All right, so here we're going to display the waiting loop. So the whole idea of the waiting loop is to wait 5 seconds. So you'll see right here, I delay 200 milliseconds for every time I check the button read. So what I'm doing is I'm waiting for 25 cycles, which is basically 5 seconds to take action. So the take action we're going to walk through here shortly as well is where it goes and looks and says, what do I need to be doing right now based on what the settings are? But I don't want to do this if the button was recently pressed. So that's why we keep saying waiting loop back to 0. And then I delay my 200 milliseconds, which is 5 times a second, and go back into the loop and do this all again. Now, one of the things you may have noticed is sometimes the button's a little sluggish. You could make this a little bit faster. It's a little bit faster. It seemed fine for what I was doing, but maybe a little bit faster would be a little bit more responsive. Just remember that if you do that, you want to like change this waiting loop count right here so that it still waits the 5 seconds. All right, so here's current settings. What this basically is going to do is return, based on the mode, what the current settings are on the thermostat. So I'm defining some variables right here. And depending on the measurement mode, I'm going to set a variable that's going to be displayed. So if it's equal to Celsius, I take the cooling and the heating temperature both, and I do the calculation. This is what Bob did, this 5 divided by 9 calculation. This is another way of doing it as well. And then you can, if it's not, and it's Fahrenheit, I'm going to come down and store that. Like I said, I store everything in Fahrenheit in the program. And then I come down to run mode, and if I'm in run mode auto, I'm going to print out @ sign, and then the cool temperature, a slash, and the warm temperature. If I'm in the fan mode, I'm not printing anything out. I'm just saying fan, and so I just send out. I return basically blank, and then if I am in cool mode, I'm just going to display U1 temperature. So it's going to be the @ sign and the temperature setting. And if I'm in heat mode, I'm going to show you the heat temperature as well as heat temperature whenever I'm in emergency mode. And in the options mode, there's nothing there either. So there's send back blank. So basically what I'm doing is, you saw this defined in the very beginning. I'm writing this variable to this temporary variable, and then I'm returning it back to the calling program above. So this does all the work. All right, so let's look at increased set temperature. And you'll see why here in a second, why I broke this out, because all this logic on the top would have been very difficult to follow. So when you call increase set temperature, I look at what mode you're in. So if you're in mode 0, which is the automatic mode, increasing is going to increase the heat temperature. So I increase the heat temperature by 1 degree for each button press. And if the heat temperature goes over the max heat type, I set it to the value of the maximum heat temperature, because you can't go above the max. If you're in mode 2, which you notice I skipped mode 1 because there is no temperature setting in the fan mode. If you're in mode 2, you're in the cool, so I'm going to increase the cool temperature by 1 degree, and I'm going to compare that to the maximum heat temperature. I'm going to use that same maximum heat number to make the maximum for the cooling as well. And if it's greater, then I set it to the maximum right there. And then we come down to mode 3, and it's heat temp. So we're actually in regular heat. So I increase the heat temperature, and again I check and see if it's over the maximum heat temperature. And I do the same thing for emergency heat. It can't go over the maximum heat as well. And you notice there's no mode 5 because there's no options needed for that. And the decrease the temperature does the exact opposite. So you see here in automatic mode, it's a degree down, takes the temperature for cool down 1 degree, and we check that here. And then mode 2 decreases the cool temperature by 1 degree. And if you're in mode 3 or 4, you decrease the heat temperature by 1 degree. And you see here, I'm looking at the minimum cool temperature. That's our range. We can't go below that. All right, so here is what I consider probably pretty much the workhorse of this program. So you saw me call this take action routine. And what this does is it determines what to do based on the current mode and the current temperature. So if we're in automatic mode and the current temperature is less than the heat temperature, then I'm going to basically do something with heat. But first thing I want to do before I do that is I want to try to compare the current temperature to the heat temperature setting minus in my case, 3 degrees set at the top. And if that is the case, I'm going to call a routine called turn on. So turn on turns on 4 things. It turns on either fan, AC, heat, or emergency heat. So in the case that is 3 degrees colder than what my current heat temperature is set to, I'm going to turn emergency heat on. So I turn the fan on. I don't turn the AC on or the heat on, then I turn the emergency heat on. So you see fan and emergency heat are turned on. If it's within that 3 degrees, so we're still in that okay area, I'm going to turn on heat, fan and heat, just regular heat. So you see a true, false, true, false. And then if that's not the case, so it's not time for heat, not time for heat. So we're going to come down here and we're going to see is the current temperature greater than what we have the AC set to. So if it's greater than the cool temperature, I'm going to turn on the fan and the AC. And if none of these conditions are true, which means we are in the good range, we don't need to be cold or heated, I'm turning everything off. So fan off, fan off, fan off, and fan off. If I'm in fan mode, there's only one thing I got to do. There's no thinking about it. I just turn this fan on. Everything else goes to false because I'm in fan only mode. In AC mode, you come down here, and if the current temperature is greater than the cool temperature, then we're going to turn on the fan and the AC. And if it's not, we're all good. We're going to turn off everything. So we're turning off everything right there. Then we come down to heat, and again, we're going to check the heat temperature. If it's colder than what the thermostat's set to for heat, then we're going to do some work. So before we do that, we determine is it 3 degrees colder or whatever the emergency heat degree is set to, then the current temperature in the current setting. And if it is, we're going to go into emergency heat. So we have fan and emergency heat. And if it's not, we're just going to do regular heat. So we have fan and regular heat. And if we're warmer or as warm as we're supposed to be, we turn everything off. So we do false across the board. And when you get to emergency heat, there's no comparing anything. Basically, if it's colder than what it's set to, we turn on emergency heat and fan. Otherwise, we turn it all off. And then the default is to turn everything off right here. If something would happen in your program that it was not one of the right modes, this would basically say, I don't know what to do. I'm turning everything off. So that's the workhorse. So the next thing we want to do is we want to look at the turn on. And basically, I'm passing in integer, they're integers. They could have been Booleans too. I probably could make it a little bit less memory usage if I would have done that. But you see I'm passing in fan, AC, heat, and emergency heat. And you see I'm adding this, I have this variable called run total. Now, the one thing I need to explain is in this program, in this routine, we're actually sending out the data for the remote as well. So before I walk through this, let's explain that protocol just a little bit. It's a very simple protocol. The format is basically this. There is a preamble of 2 X's, and then there's either 1s or 0s for the next 4 characters, which determine if the fan, AC, heat, or emergency heat are on or off. Then there's a Y, which is the stop, and then there's a checksum, and then there's a Z for a terminator. So you should always get something that's XX, and then either 0 or 1s, a Y, another number, and then the Z. This other number is a checksum. And the way it's done is each of these positions has a value. So the first position is equal to 1, the second position is equal to 2, the third one's equal to 3, and the fourth one's equal to 4. I know, not very original, but this works real easily. And whichever ones are turned on, you add them together. So if the fan and the AC is on, you're adding 1 and 2 so that this checksum will be equal to 3. So when I receive this on the receiving side, which we're going to walk through after this program, I compare that to make sure that I'm getting everything in the right format so that I'm not turning something on that shouldn't be turned on because I got garbage. Just another way of checking to make sure that it was received properly. So as we walk through this, you see the first thing I do is I send out a preamble. And I check and I see is fan supposed to be on. So if it's supposed to be on, I go ahead and turn the fan pin on. So there I set the fan pin equal to true. And I'm going to send out a 1 because the fan should be turned on. And my run total is now equal to 1, which is this is the checksum. So the checksum is currently equal to 1. And in the case where the fan isn't supposed to be running, it comes down here and it says the pin is off. And I send out a 0 because 0 means that this function is not running or not on. Then I come down and check the AC, and again, I turn on the AC pin to true, and then I send out a 1, because I've already sent out the 1 or 0 for the first one, so now we're in the second one. And then my checksum is going to get added to by 2 now, because I'm in the second position. And if it's not on, then I turn off the pin, and I send out a 0. Then we come down, we check heat, we do the exact same thing. If heat is true, then we turn the pin on high, send out a 1 for that position, and since it's a 1, we add 3 to the checksum. And if not, we send out a 0 and turn the pin off right here. It would do the same thing for emergency heat, exactly the same. You notice run total is equal to 4, so I've added up all these run totals to come to the end. Now I send out the Y, which is the stop, and then I send out the checksum, and then I send out the terminator right here. And that's it. That's it for the sender. It's a little longer. The one I'll have to walk through, but what I want to do now is I want to go over and I want to show you the receiving code. It's much simpler than what the sending code is, because it basically is getting information back as to do. There's no decision making in this one. So you see again we have our pins defined. You notice there's a lot fewer pins. I have a fan, AC, heat, and emergency heat pin, the exact same pins that are on the other sketch, so you can pretty much take the same connections out of the Arduino as you would for the other program. And here you notice we have a state. So instead of a mode, this one has a state, and we've talked about state machines before, which is kind of what the mode is in the other program, but here we're actually going to call it a state machine, and I can't remember what episode I talked about that in. So we have basically 5 states, and this is all based around the protocol. We have a begin, we have a start, we have a values, we have a checksum, and we have end transmission. Basically, the begin is when I'm looking for the X's to come across for the preamble. After I see an X, I'm going to go to the start, and I should see another X. So that's how the preamble is working. And then after I see the second X, I'm assuming what's coming next is values that I need. So I keep reading values until I get to that Y. When I see that Y, I go into checksum mode. So I'm waiting for my number for a checksum. And then when I see the Z, I know I'm at the end. So these are the states, and you're going to see how I'll walk through the states to validate where I am through all this. And then here I have some things that I'm using throughout the program, you'll see. And setup's much simpler. Basically, it's 4 pins set up all to output, and serial begin 9600 because I'm receiving my commands via serial port from the XB. All right, so here we come down and we loop, and if you've seen some of the other things I've done with serial use is very similar. I define a input character, and I check if data is on the serial port, and if it is, I go ahead and I read it, and I stick it into this CH variable, and here comes the state machine. So if we're in the begin state, all I'm doing right here is looking for an X. So I'm going to keep reading serial data until I see a capital X. When I see the capital X, I'm going to say, okay, I'm starting. So I'm going to set my current state to start and drop out of this case statement. And next time around, it's going to come back in, read another character, and it's going to come down to start. If it's another X, then I'm assuming, okay, we're probably getting ready to go get real data because I've gotten 2 X's in a row, which is what I'm looking for. So I set my current state equal to values, which is the next thing we're going to do. And I set my value pointer equal to 0, which is basically saying the next thing I read should go into array element 0. And if something happens that I don't get an X, so we say we're getting garbage, and one of the things that comes across is a capital X in the garbage, and the next thing's not a capital X, I'm going to say that wasn't the beginning. So I'm going to go back, I'm going to start over again and say look for an X to begin with. So even if you were sending valid data across and you got an X and some other weird character and then the numbers, it would ignore it because it doesn't know, it's not positive what it got was correct. So it's going to go back and start over, and then in 5 seconds when it sends it again, it'll get the new information. All right, so we come down in the values. So we get 2 X's. We're now in the values. So I'm assuming I'm getting the numbers, the ones and zeros come across. And I'm coming down here, and the first thing I'm going to check for is, am I getting another X? And if I'm getting another X, something's wrong, because it shouldn't be getting an X right now. So I'm going to go back and do begin. If I get a Z, which is end transmission, something's wrong there too, because I shouldn't be getting that. So I'm going to go back and I'm going to start over. And if I get a Y, I assume that I've gotten all the numbers, and I'm going to go into checksum state. So if none of these conditions are true, so we're still probably getting numbers, I'm coming down here and I'm checking, is it really a number? So is it between 0 and 9? And it really should be between 0 and 1, because I'm only really sending over 0 and 1. So I could tighten this down a little bit and just make that 1, make it a little bit cleaner probably, but I'm not going to change it right now. So if it is, I'm going to go ahead and save to the values array, to the value pointer, the character, which is either a 0 or 1, increase the value pointer. If the value pointer goes greater than 4, I'm going to start over again because I shouldn't get that many numbers. I know I only have 4 numbers coming to me. If I get 5, something else is wrong. So again, I'm going to start over. It's just another condition. It says something's wrong. You need to start over. So after we do this and we go through this loop and get all 4 of these, we're going to get this Y at the end. So it should be XX, 4 numbers, and then a Y. So when I get that Y, I'm going to go into checksum mode. So I'll come down here to checksum. And there's basically 2 things. I'm either going to get a Z or a number. I should get a number first. So hopefully I get a number first. I'm setting the checksum equal to that. And then I get a Z saying it's the end of transmission. And when I get the end of transmission, I basically know I'm at the end. So I go into the end of trans state. And I come down. And the next time through, basically there's a character turn line feed that follows this. So there will be another character that I just read in. And it comes down here and it says, is checksum equal to calc checksum? And I'll show you that routine in a second. And if it is, it's assuming that everything it came across was valid. So at that point, I'm basically calling the same turn-on routine that we have in the other one, with just a few things taken out of it. And I'll show you that in a second as well. But I'm sending it the values that were passed over. So all I'm doing is saying, if the value I got was equal to 1, then send true over. Otherwise, send it to false. To the turn-on value. And then I start over again, set my state back to begin, and I'm back waiting for another X. So let's go down and look at calc checksum. And as I showed you in the other one,
Mike, I've got a question for you before you get too far, because while I've been listening to this, I've been thinking about, well, what happens if you get noise? And because you're doing this, these are ASCII characters you're sending, correct?
Yes.
That are being transmitted.
Yep.
So to get an X in just random noise, you'd have to get, ASCII characters. There's 128. No. Yes.
Yeah, it should be
128 characters in the basic ASCII set.
Right.
So you have a 1 in 128 chance of getting a random X, and then the next character, another 1 in 128 random chance of getting a capital X.
Right.
Correct?
Yes.
Which would be 16,000, whatever 128
right,
squared
and then it
is.
goes farther, then checking if I'm getting something other than a letter as well, or a number on the next 4.
So all of this is making sure that you never get random noise data being transmitted and received in the wrong order, because the odds of getting random noise in the right sequence is virtually, well, you're probably more likely to win the lottery than to get this right. Okay, well, I just wanted to make sure that I was understanding, and that's good, because you've got all these checks. You're checking each character. You've got a checksum, because the last thing you want to do when you're receiving the data at the other end is to end up with incorrect data and turn on and off.
Right, exactly. You don't want your heater turning on for no reason at all, because your neighbor turned on the microwave for, whatever.
That's right.
All right, so let's go look at calc checksum. So on the other side, you saw me adding a value of 1, 2, 3, and 4. I'm doing the same thing here, the exception of I'm doing it in a loop. So you see I'm going 0 to 4, and I'm checking if it's equal to 1. And if it's equal to 1, I'm basically adding to the value this loop value right here. So that's how I get the total. And then I return 48 plus. This is how I'm getting it into the ASCII range right there. And then we have our turn on routine, and this is basically a copy of the other side, minus the fact that this side doesn't have the protocol information going out. So all I'm doing right here is if fan is on, I'm turning the pin true or false, depending on what the value of the integer is. Same thing with AC, heat, and emergency heat. And that's it. That's all there is for the remote side. Now, there is something that I wanted to go back to the actual Arduino. So originally I was going to do this with relays, and I don't have relays to fit my breadboard, so I ended up using LEDs. But you'll see in here that we actually have transistors, and the reason we do this is the Arduino can't drive that many relays. There's not enough power for it, so we're using the transistors to get around that. Now I think I actually have a drawing for it. Do I still have it here somewhere? And we'll show you how we actually put that in there. That's something I probably should have mentioned before, is you don't want to go directly to the relays. Let's see if I can get it up here quick. I guess it depends on how quick is. Do I have this? Yes. Okay, so here's the schematic. Let me go over this. Here's the schematic, and you'll see right here we are coming out of the Arduino on these digital pins, and we are going into the base of the transistor, and then we're right now running LEDs, but you could just as easily stick in here a relay, and this would not take the draw or draw too much out of the Arduino. Do you know what the maximum draw is on the Arduino pin?
50 milliamps, if I remember correctly.
Yeah, it's pretty small.
With a total of the Arduino,
like 250 or something like that.
I think it's 500 you can draw. Functionally, it's 450 because if you're running off a USB, you can't run more than 500 milliamps off of a USB hub. So
right.
You're really, to include some current for the Arduino itself, you're looking at pins with 450 total. Right.
So yeah, we basically would replace these LEDs with relays in the case you want to do that. Now, that was my original intention. I just didn't have relays that would fit. It seemed like my relays are all the way they're laid out with the pins. You're crossing sides or something with them, and this doesn't work right. So I just didn't have a chance to get it to work. All right, that's it for that.
That's good. That's good code. And whether my example was just reading data off the analog pin, you could read off a digital pin, analog pin. The rest of the control for a HVAC system is the same. Of course, you've got to be careful. You got to know what you're doing before you implement anything that we've demonstrated tonight.
Yep, be very careful, especially if you're working actually in the HVAC unit itself, because there's some high voltages in there, very high voltages. All right, so I want to remind you again that our YouTube channel is moving to youtube.com/TechZenTV. If you're watching Let's Make It, go there now. I mean, we're at the end of the show now. You go ahead and go there now and hit subscribe, and so we don't lose when our new shows come out. If you're watching us from somewhere like iTunes or any of the other podcast directories, they all have these rating systems in them where you can go in and leave a little comment and give a rating. Definitely would appreciate if you go out there and give us, a nice rating and a comment that helps us get found in all of these. I mean, we're getting more and more viewers all the time, and we're getting more and more questions, and we love that. So we just need some more help to try to get the show to grow a little bit. So if you can take a couple minutes and go out and give us a rating and a couple comments out there, that'd be definitely appreciated. Everything we showed you today will be on the show notes, and that's actually all at techzen.tv. You can also go to letsmakeit.tv. It takes you to the same place. And every show has a page with notes, and we're getting more, and we're going to be using fritzing, which we showed you here. And maybe we'll start putting more of this out there as well with the schematics and different diagrams and things like that. The code will all be out there, and the links to the code will be out in the show notes as well at techzen.tv. And if you just found this show and you're interested, if you go to techzen.tv and go to the show page, you can see all the old episodes. This is episode 25. So we have 24 more great shows prior to this one that you can go out and you can watch as well. All right. Anything else,
if you've
Paul?
got a question, ask.
Yeah, most definitely.
Questions.
Yep, and we're getting more of them, so people are getting much more comfortable with asking us questions, and we love that stuff. Plus, if you have other show ideas, things you want us to do, send those as well. We got a good one this week with some requests or ideas for future shows, and we definitely love that input. It's great.
That's right.
Anything else, Bob?
I think that's it for tonight.
All right. Well, thanks, everybody, and we'll see you all next week.
Thank you.
For show notes for this show, contacts, and more, go to the techzen.tv website, where you can get show notes for all of our shows. We love to hear from our viewers and listeners. We have an email, a Twitter, and a phone number where you can contact us for each show. For details, visit the techzen.tv website and get the show details. You can also make a video and upload it somewhere like YouTube or Vimeo, and then just send us a link. You never know, you may see your video in a future show. You can get all of our shows delivered automatically to your favorite device by going to your favorite podcast website like iTunes and subscribing. Each of our shows also has a YouTube channel you can subscribe to get regular updates. Our shows are also available on most internet radio networks like Stitcher and TuneIn Radio. You can also watch and listen to our shows on Xbox, TiVo, and Roku. You can even find us on your Zune.